Hello and welcome to my YouTube channel. Today in this video, we are going to talk about Superloop programming versus task programming in real-time operating system, and what is the difference between the Superloop programming technique and the techniques that are used to write tasks in real-time operating system. So first of all, let us talk about the basics of Superloop programming. In any embedded system, the programmers generally prefer to write a program without any exit loop. Remember, in embedded programs, the programs generally do not have exit loop. So that means these programs do not terminate anytime. So they will continue for infinite time period. Second, unlike application programs in normal operating systems, most embedded MCU based applications start at power on. Okay, so at power on, the program will automatically start and they end abruptly when the system is powered off. So remember, whenever we power off the embedded system, programs end abruptly. We do not have any sequence for shutting down the programs which run in embedded systems. Therefore, embedded applications typically do not have any of shutdown tasks normally associated to any applications. In general, whenever we use other applications in other operating systems, whenever we apply for shutdown, those applications free the memory and free the other resources, whereas such freedom is not available in case of embedded systems. Now let us talk about how the super loop actually is executed. So we will have a main program inside which we will have a while one loop. So you can see the loop is while one. It means this will run for infinite time period. And how this function while loop will execute? First, the function 1 will run and take the CPU resources to complete its job. Then it will hand over the CPU resources back to function 2. Function 2 will take its own time to complete its function, then release the CPU resources which will be taken by the function 3, and after completing its job, function 3 will also release the CPU resources, and then again this loop continues. So therefore, again function 1 will start, take the CPU resources, release the CPU resources, function 2 will start, and so on. So this cycle will continue for infinite time period in case of super loop and embedded systems. Let us take an example. In the main function, we first initialize the system by using an initialization related function. Then after that, we enter into the while one loop or infinite loop, in which we have three different functions. The first function checks the device status, second function processes the device data, and third function outputs a response from the device. And then again this cycle will keep on continuing for infinite time period. This is the basic approach used in Superloop programming. Let us talk about Superloop programming in real-time operating system. So here this block diagram shows the approach that is used by Superloop programming when function 1 takes the CPU resources, completes its job, gives the CPU resources to function 2, then function 2 completes its job, it releases the CPU resources after completing function 2, then function 3 will take the CPU resources, and so on. So this cycle will keep on running for infinite period. Such an approach is generally called super loop, and any main loop that never returns is generally referred to a super loop. This type of setup is perfect, or we can say good enough, for simple programs where function 1, function 2 and function 3 do not take too much time, and we are not worried about the time related constraints. In such cases, we can go for super loops. For simple tasks with no timing constraints, one can rely on super loops. It is not necessary that you always should go for real-time operating system, design task and handle all the events using task. Instead, if there is no timing constraint for any project, in that case, we can rely on super loops because they are easy to write and easy to deploy. So when simple super loops are operating quickly, then you don't need to go for real-time operating systems. Now let us talk about why the real-time operating systems are required, or where these real-time operating systems are required, and why super loops are not considered always a good option. So for any embedded system, time is one of the most important feature. So always we try to design a system which should complete its overall job within a prescribed time. So let us take the same example where we were having three functions: function 1, function 2 and function 3. In any embedded system, clock is one of the most important feature which actually decides the speed of execution of the program. And this clock will continue to run till we shut down the system or power off the system. So assume function 1 and function 2 are running and they take their share of CPU resources and time to complete their job. And suppose function 3 is dependent on an external event, maybe pressing of a switch or any other event. And if the event takes place, then of course function 3 will execute. So suppose this function or the external event took place after the function 2 started its job. So since the external event took place before completion of function 2, function 3 will be executed after the completion of function 2. So we can say indirectly that function 3 waited for a very small delay after the external event was generated. Second time, assume after completion of function 3, function 1 completed its job, function 2 completed its job, but there was no external event between function 1 and function 2. And this caused the function 3 not to execute. And now again function 1 started its job and the external event was generated in the middle of function number 1. Now in such case, the function 3 will have to wait for a longer period, or we can say the delay will be longer, because now the function 1 will complete its job, release the CPU resources, function 2 will take the resources, complete its job, then it will release the resources and function 3 will take the CPU resources. Now here we can see the delay is longer compared to delay number 1. And after completion of function 3, it will give the resources back to function number 1. And suppose function 1 this time takes some extra time to complete its job. In such case, Now, even if the external event is generated in the middle of function number 1, because function 1 took extra time to complete its job, function 3 will have to wait further for a longer delay. So here we can see that function 3, which is dependent on an external event, has to wait for 3 different delays depending on when the function external event was triggered and how long the function 1 and function 2 took to complete their jobs. So therefore, one cannot predict how long function 3 will have to wait because these 3 delays are different. Such a phenomenon or changes in the delay is called jitter. Suppose an external event is triggered and function 3 gets to complete its job in a very short time period, then we can call it a minimum delay. But it may happen that this delay may vary depending on the occurrence of external event or the time taken by the function 1 and function 2. So function 3 is dependent on these two factors, and because of which the function 3's occurrence cannot be predicted timely. Such a phenomenon is called jitter, and programmers always try to avoid jitters in their program. Why? Because in such a system we cannot assure the timeliness, or we cannot say when the function 3 will be executed. To avoid jitters, we generally use interrupts. So the previous example was an example of super loops waiting for the external event to trigger, and such an approach is called polling, where the CPU or the resources keep on checking whether the external event is generated or not, and polling for a single event can be considered as wastage of microcontrollers time and resources. So we always try to avoid polling based programming. To avoid polling, microcontrollers uses dedicated hardware to attend very important events, and those hardwares are called nested vector interrupt controllers, or we can say interrupt controllers. Every ARM Cortex microcontroller uses interrupts to handle urgent events. It is not only about ARM Cortex microcontrollers. Every decent microcontroller or any good microcontroller will always use interrupt to attend important events. Interrupts are such a critical piece of functionality that ARM Cortex-M core provides a standardized peripheral for it, and we call it NVIC, or in full form nested vector interrupt controller. Now let us compare the difference between Superloop and tasks in RTOS. In easy word, task in RTOS can be compared with loops in the main program. We can compare them, but there are some subtle differences between these two. Tasks are simply C functions that never exit. As such, they are implemented as an infinite loop. So there are two major differences between the task and a function in a loop. The first difference is that tasks in real-time operating system have their own separate stack memory. This is a very important feature. Every task in real-time operating system will have its own separate stack memory, which will not be shared with any other task in the system. Second, Tasks in RTOS have different levels of priority, whereas functions in a super loop do not have their level of priorities. Whereas in case of task, we have different level of priorities assigned, and based on which the scheduler of the real-time operating system decide which task should be completed prior to other tasks. In future, we will see how to write functions related to tasks, and how can we set the priorities, and how can we write a program in RTOS to do simple jobs, and later complicated systems can be designed using RTOS. With this, I would like to end this presentation. If you have not subscribed the channel, then I would request you to please subscribe the channel and press the bell icon so that you will be notified as soon as I upload a new video. If you have any suggestions or comments, then do share your suggestions and comments in the comment section. Thank you and have a nice day.